This is a video for OCR Pure Core Mathematics. Second order differential equations 1, homogeneous equations, 1.5, auxiliary equation with repeated roots. In a previous video in this sequence, we looked at this differential equation and found that it can be solved by using the auxiliary equation like this. And we looked at what happens if the discriminant b squared minus 4ac was greater than 0. In other words, if we got two distinct real roots. If I call those roots lambda 1 and lambda 2, then we would get this general solution. In this video, we're going to look at what happens if the discriminant b squared minus 4ac is equal to 0. So we get a repeated root or coincident real roots, and I'm going to call those lambda. Now this would give us a complementary function of the form a e to the lambda x. But as it's a second order differential equation, we would need two arbitrary constants. Now we can go through and show that by differentiating, y is equal to bx e to the lambda x is another possible solution. And so our general solution is to use a plus bx e to the lambda x. So let's find the general solution of this differential equation. Well, I start out with my auxiliary equation, which is going to be m squared minus 6m plus 9 is equal to 0. Now this factorizes to m minus 3 squared equals 0. And this means I get m equals 3, and it's repeated. So my general solution then, using the strategy we saw on the previous slide, is to write y is equal to a plus bx times e to the 3x. So this involves two constants, and I brought the second constant in with an extra x. There's that written up more tidily for you. There's my auxiliary equation and my repeated solutions, and therefore my general solution. So let's have a look at a plot of some of the solution curves. I've got two here plotted for you, one where a equals 1 and b is minus 1, and one where a is minus 0.2 and b is 0.1. Although they look very different, there are some similarities. For instance, if we look at these points, these are points where y equals 0, then they turn out to be when x is equal to minus a over b, that initial bracket here being 0. So here we would expect to get an intercept at 2, and we do, and here we'd expect one at 1, and indeed we do. Second thing to notice is what happens for large values of x. So as x tends to infinity, y, well, it depends on the value of b. It'll either tend to infinity if b is greater than 0, or it'll tend to infinity if b is equal to 0. In fact, it's just y is equal to a to the 3x, so it's tending to a to the 3x. Or it will tend to minus infinity if b is less than 0. And you can see here that's what's happening there. And here it's tending to plus infinity. What happens as x tends to minus infinity? And again, it depends on the range of values for b. If b is greater than 0, then y will tend to 0, but it'll do it from below. If b is less than or indeed equal to 0, y will again tend to 0, but from above. And in fact, In the situation where b is equal to 0, then there is no x value for which y is equal to 0. Let's have a look at a dynamic plot of that. This is the parameters for the left-hand graph, and I can adjust them to give me the parameters for the right-hand graph. So drop this down to minus 0.2 and this one up to 0.1, and there we get the right-hand graph. Now we could just check some of these. So what happens when b is positive? Well, if b is positive, as it is here, then as x tends to infinity, y tends to infinity, and whatever the positive value, that's going to keep happening. If b is negative, then as x tends to infinity, y tends to minus infinity, and we've seen that from this bit here as well. So what about the situation in which b is equal to 0? You can see there it's actually just behaving like a e to the 3x. So if a is positive, it's just like a multiple of e to the 3x, and if a is negative, then it's just the mirror image of that. The other thing to look at is what happens if b is actually quite large. As a equals 1, let's push b right the way up. And you'll see here that what happens is the graph comes down, cuts through, and then tends to 0 from below. Whereas if b is negative, it comes up, cuts through here, and then tends to 0 from above. The next video in this sequence is 1.6 auxiliary equation with imaginary roots.